Have you ever wondered, why can't you walk through walls? It's not because the wall is too solid, too hard, or too real. It's because the electrons in your body refuse to touch the electrons in the wall. They don't collide. They don't overlap. They simply don't like each other. And tonight we're going to explore why. Where are you listening from right now? And what is the feeling of your room? Quiet, dim, rainy, or warm? While we share this small moment under the same sky. If this calm finds you and you enjoy these soft explorations into the mysteries of science, you're welcome to stay a little longer, maybe leave a quiet, like follow along with a subscribe, or simply rest here as we drift together. So let's begin. Right now you think you're sitting on a chair, but in truth, you're floating. Feel the chair beneath you, the weight of your body settling into it, the solid pressure against your legs, your back, your hand holding your phone fingers wrapped around its edges. It feels real, doesn't it? Firm, undeniable, the kind of sensation you've trusted your entire life. But here's the truth that physics whispers in the dark. Not a single atom in your body is actually touching the chair. Not one. The electrons in your skin and the electrons in the chair's surface are repelling each other, pushing away with invisible electromagnetic force. You're hovering, held up by nothing but the mutual refusal of tiny particles to occupy the same space. The solidity you feel is an illusion, a kind of gentle lie your senses tell to keep you calm. In fact, if you could see yourself at the atomic scale, you'd discover something unsettling. 99.9999% of your body is empty space. The nucleus of each atom, where almost all the mass lives, is unimaginably small. If an atom were the size of a football stadium, its nucleus would be a grain of sand at the center. Everything else, the vast bowl of seats stretching out in all directions, is just void. And yet you feel solid. You feel real. This strange resistance, this refusal of matter to pass through matter, comes from a rule called the Pauli exclusion principle. It's simple, almost stubborn in its elegance. Electrons, those tiny, negatively charged particles orbiting every atom, refuse to share the same quantum state. Imagine a movie theater where every seat can only hold one person. No doubling up, no squeezing in. Each electron demands its own space, its own arrangement of energy and spin. And when two atoms come close, their electrons push back, not with force in the classical sense, but with quantum insistence, a boundary that says firmly and without compromise, no further. That's why you don't fall through the floor. Not because the floor is hard, not because it's dense or strong, but because the electrons in your feet and the electrons in the ground beneath you are incompatible. They occupy different states, and they will not budge. This quantum pressure, invisible and tireless, holds you up against gravity itself. Now here's the strange part. Mathematically, it is possible for you to walk through a wall. Quantum mechanics allows for it. Every particle in your body could, in theory, align perfectly with the gaps between particles in the wall. The probability isn't zero, but it's so breathtakingly small, something like 1 in 10 to the power of a number with more zeros than there are atoms in the observable universe, that even if you tried once every second since the Big Bang, you still wouldn't have had enough time. So you remain here, suspended, not quite touching anything, held in place by the quiet electric refusal of the universe to let things overlap. But if you're not really touching anything, then what are you touching? Everything you've ever seen is a lie. Light has always been a shapeshifter. For more than 300 years, scientists argued over what it truly was. Isaac Newton, in the 17th century, believed light was made of tiny particles, corpuscles, little bullets of brightness flying through space. Around the same time, Christian Huygens imagined something entirely different. To him, light was a wave spreading outward like ripples on water, bending around corners, washing over obstacles. Both were brilliant. Both were wrong. Or rather, both were half right, in ways that would take centuries to untangle. By the 19th century, the debate seemed settled. Thomas Young's double-slit experiment in 1801 was elegant and devastating. He shone light through two narrow slits and watched as it painted a pattern on a screen beyond. Not two bright bars, as particles would make, but a series of bright and dark fringes, interference, the signature of waves overlapping, adding together in some places, canceling out in others. Light, it seemed, was a wave. Case closed. Or so they thought. Then came 1905, and Albert Einstein, a young patent clerk, with a mind that refused to accept easy answers. He was studying something strange, the photoelectric effect. When light strikes a metal surface, it can knock electrons loose. Classical wave theory predicted that brighter light carrying more energy should always free more electrons regardless of color. But experiments showed something else entirely. Only light above a certain frequency could eject electrons. Dim blue light could do it. Intense red light could not. Einstein proposed something radical. Light's energy doesn't spread smoothly like a wave. It arrives in packets, discrete bundles of energy he called quanta. Later, these would be known as photons. Each photon carries a specific amount of energy, determined by its frequency. Blue photons pack more punch than red ones. It doesn't matter how many red photons you throw at the metal. If each one is too weak, nothing happens. But a single blue photon, with its higher energy, can knock an electron free in one sharp blow. Light, Einstein said, behaves like particles. He won the Nobel Prize for this insight, not for relativity, but for showing that light could hit like a boxer, not wash over like a tide. And yet the wave experiments didn't go away. Light still created interference patterns. It still bent and diffracted. So, which was it, particle or wave? The answer, as quantum mechanics would reveal, is both, and neither. It depends entirely on how you look. The double-slit experiment, when performed with single photons, becomes truly haunting. Imagine firing one photon at a time toward the two slits. Each photon is alone, no other light to interfere with. And yet, over time, as thousands of photons strike the detector, one by one, the same interference pattern emerges. Bright fringes where they land often, dark gaps where they never seem to go. How each photon appears to pass through both slits at once, interfering with itself as if it were a wave spread across space. But when it lands, it makes a single dot, a particle, localized, definite. One photon, one click. Now here's where it gets unsettling. If you place detectors at the slits to watch which path each photon takes, the interference pattern vanishes completely. Instead, you get two simple bars, exactly what you'd expect from particles traveling through one slit or the other. The photon somehow knows it's being watched. And when observed, it stops behaving like a wave and commits to being a particle. Does the photon sense the detector? Does it know you're looking? Not in any conscious way, but the act of measurement, of interacting with the environment, forces the quantum system to choose. The wave of possibilities collapses into a single outcome. Reality doesn't decide what happened until it must. Einstein hated this. He once asked, only half joking, "Do you really believe the moon isn't there when you're not looking at it?" Quantum mechanics taken seriously suggests something almost that strange. Not that the moon disappears, but that asking where it is changes what kind of answer you can receive. And it's not just light. In 1924, a French physicist named Louis de Broglie made a bold proposal. If light, which everyone thought was a wave, can behave like particles, then perhaps matter, which everyone thought was particles, can behave like waves. He calculated that every object, every particle from electrons to baseballs to you, has an associated wavelength determined by its momentum. For large objects, the wavelength is impossibly tiny, far too small to detect. But for electrons, it's significant. And just a few years later, experiments confirmed it. When beams of electrons were fired at crystals, they scattered in patterns identical to light waves diffracting through a grating. Matter, it turned out, wasn't solid little spheres. It was waves of probability spread out in space, collapsing into points only when measured. So, what is waving? Not a physical substance, not water or air, but something deeper, a probability field, a mathematical description of where a particle might be found if you ever bothered to look. Before measurement, the electron doesn't have a position. It has a cloud of possible positions weighted by likelihood. After measurement, one location becomes real. The rest vanish like paths not taken in a story that only writes itself when read. Light behaves as a particle when you measure it that way, as a wave when you don't. The same is true for electrons, for atoms, for anything small enough that quantum rules apply. The universe doesn't choose what it is until you ask, and the question you ask determines the answer you receive. If light can be both wave and particle neither, and both depending on the moment, then what is reality really? So light lies, matter floats. But the strangeness doesn't stop there, because in the quantum world, something can be two things at once, until you force it to choose. There is a cat, it is both alive and dead, and it will remain in that state until you open the box. This is not a riddle. It's not a metaphor. It's one of the most famous thought experiments in all of physics, and it reveals something deeply unsettling about the nature of reality itself. The idea is called superposition, and it tells us that at the quantum level, things don't simply exist in one state or another. They exist in many states at once, a delicate balance of possibilities that only collapse into a single outcome when observed. Imagine flipping a coin. In the classical world, even while it spins through the air, the coin is either heads or tails. You just don't know which yet. But in the quantum world, before it lands, the coin isn't hiding a secret answer. It genuinely is both heads and tails at the same time, not one or the other, both superimposed, a blend of contradictory realities held together by the mathematics of probability. This principle, strange as it sounds, is what allows quantum mechanics to work. a particle doesn't have a definite position until you measure it. An electron doesn't spin purely up or purely down until something forces it to decide. Before measurement, it exists in a cloud of potential outcomes, each one weighted by probability, all humming quietly in the background of reality. In 1935, the Austrian physicist Erwin Schrödinger wanted to show how absurd this idea would be if scaled up to everyday life. So he designed a thought experiment, dark and memorable. Picture a sealed box. Inside the box is a cat, very much alive at the start. Also, inside is a small amount of radioactive material, a Geiger counter, a hammer, and a vial of poison. The radioactive substance has a 50% chance of decaying within 1 hour. If it decays, the Geiger counter detects, it triggers the hammer, which smashes the vial, releasing the poison. The cat dies. If the atom doesn't decay, nothing happens. The cat lives. Now, according to quantum mechanics, before you open the box, the radioactive atom exists in a superposition. It has both decayed and not decayed. And if the atom is in superposition, then so is everything connected to it. The Geiger counter has both clicked and not clicked. The hammer has both fallen and not fallen. The vial is both broken and intact, and the cat, poor creature, is both alive and dead at the same time. Schrödinger created this scenario to ridicule quantum mechanics, to show that its rules, when pushed to the macroscopic world, led to nonsense. A cat cannot be half alive and half dead. That's absurd. And yet the mathematics of quantum theory insisted it was true. The cat exists in a superposition of life and death until the box is opened, until an observation is made, forcing the system to collapse into one outcome or the other. The moment you lift the lid, the wave function collapses. The universe is forced to choose. The probabilities sharpen into a single reality. You see either a living cat or a dead one, never both. But before that moment, quantum mechanics says both possibilities are real, not potential, not hypothetical, real in a strange, suspended way that defies intuition. Why does opening the box matter? Why does observation cause collapse? No one fully agrees. Some say the act of the measurement, the interaction between the quantum system and the environment, entangles them, irreversibly spreading the information outward until the delicate superposition is lost. Others suggest consciousness itself plays a role, though most physicists are uncomfortable with that idea. What's clear is that the quantum world allows ambiguity, but the classical world, the one we live in, does not. This isn't just philosophy. Superposition is real, and we use it. Quantum computers, the next frontier of technology, are built entirely on this principle. A classical computer bit is either 0 or 1. A quantum bit, a qubit, can be both 0 and 1 simultaneously held in superposition. 2 qubits can represent 4 possibilities at once. 3 qubits, 8. The growth is exponential. By the time you reach 300 qubits, you're holding more simultaneous states than there are atoms in the observable universe. That's why quantum computers can, in theory, solve certain problems that would take classical machines millions of years. They explore all possible answers at the same time, then use interference, the same wave behavior that creates patterns in the double-slit experiment, to amplify the correct solution and cancel out the wrong ones. It's computation by superposition, by holding many realities in hand until one is needed. But superposition is fragile, heartbreakingly so. A single stray photon, a slight vibration, even the faint warmth of the environment can disturb the delicate balance. When that happens, the system decoheres. The superposition collapses. The qubit becomes an ordinary bit stuck in zero, or one no longer capable of exploring multiple paths. This is why quantum computers must be kept colder than outer space, shielded from every tremor, every whisper of interference. Maintaining superposition long enough to perform a calculation is one of the greatest engineering challenges of our time. And it's why you don't see cats both alive and dead. Schrodinger's cat, if it were real, would decohere almost instantly. The cat is warm, it breathes, it interacts with air molecules, with light with the walls of the box. Those interactions leak information into the environment, collapsing the superposition long before you ever open the lid. The quantum world is real, but it doesn't survive contact with the messy, noisy, classical world we inhabit. Still, the question lingers. If observation collapses the wave function, if measurement forces reality to choose, then who is observing the observer? Superposition shows us that reality is uncertain until measured. But there's a deeper rule at play, one that says, even with perfect instruments, there are things you simply cannot know. There are questions the universe forbids you to ask, not because you lack the intelligence, not because your tools aren't precise enough, but because the answers do not exist. This is the heart of the Heisenberg uncertainty principle, one of the most profound and misunderstood ideas in all of physics. It tells us that certain pairs of properties, position and momentum, energy, and time cannot both be known with perfect precision at the same moment. The more accurately you measure one, the fuzzier the other becomes. Not due to clumsy instruments or experimental error, but as a fundamental law of nature woven into the fabric of reality itself. Imagine trying to find a fly in a dark room. You can't see it, so you turn on a flashlight. The beam of light made of photons bounces off the fly and into your eyes. Now you know where the fly is. But here's the problem. Those photons, tiny as they are, carry momentum. When they strike the fly, they give it a little push, changing its velocity. The brighter your flashlight, the more photons you use, the more precisely you can pinpoint the fly's location. But each photon nudges it a bit more, blurring your knowledge of how fast it's moving and in which direction. You might think, well, just use gentler light, dim the beam, use fewer photons, and you'd be right, that reduces the disturbance. But dimmer light gives you a fuzzier image. You lose precision in measuring position. There is no way around it. The act of knowing where something is changes how well you can know where it's going. The two pieces of information are linked inversely by a constant so small it's almost incomprehensible, yet so fundamental it defines the grain of the universe. That constant is Planck's constant, roughly 6.6 times 10 to the negative 34. It's the smallest tick on nature's clock, the quantum of action, the measure of how grainy reality is at the smallest scales. If Planck's constant were zero, the universe would behave classically. You could know everything, predict everything, measure position and momentum to infinite precision. But it's not zero, and so the universe is blurry at its core, not because of ignorance, but because of its own nature. This isn't a failure of measurement. It's not a technological limitation. The electron doesn't have a precise position and momentum waiting to be discovered. Those properties simply don't exist simultaneously in a well-defined way. Before you measure, the electron is a wave of probability spread across space. That wave has a wavelength which relates to momentum and a spread which relates to position. A tightly localized wave, one that tells you exactly where the particle must be built from many different wavelengths, meaning many different momenta. A smooth, uniform wave with a well-defined momentum must be spread out in space, meaning an uncertain position. The uncertainty principle is geometry. It's the mathematics of waves, and particles being waves must obey it. Now here's the strange consequence. This uncertainty is what keeps atoms from collapsing. If an electron could be pinned down precisely inside the nucleus, occupying a tiny, well-defined space, its momentum would become enormous, according to the uncertainty principle, so large, in fact, that it would blast out of the atom entirely. The electron can't settle too close to the nucleus, because doing so would make its speed too uncertain, too energetic. There's a minimum size, a radius, below which the electron simply cannot be confined. That minimum size is the atom. Uncertainty doesn't destroy structure, it creates it. Without this principle, matter would implode. Electrons would spiral into nuclei, atoms would vanish, and the universe would collapse into a dense, featureless soup of energy. The blurriness of the quantum world is what gives reality its shape, its stability, its refusal to fall apart. And it doesn't stop at position and momentum. Energy and time are linked by the same rule. The shorter the time interval over which you try to measure a system's energy, the more uncertain that energy becomes. This opens a loophole in the conservation of energy, not a violation, but a brief allowance. For incredibly short periods of time, the universe can borrow energy from nowhere, creating particles out of pure vacuum, as long as they disappear quickly enough that the debt is repaid. These are called virtual particles, and they flicker in and out of existence constantly everywhere, even in the darkest, coldest, emptiest regions of space. The vacuum, then, is not silent. It hums, it seethes with quantum fluctuations, tiny eruptions of energy that appear and vanish faster than anything could ever detect them directly. And yet their effects are real. They nudge electrons in atoms, creating tiny shifts in energy levels that have been measured to extraordinary precision. They generate forces between objects, pulling metal plates together in experiments that confirm the vacuum's restless energy. Even empty space refuses to be still, because if it were perfectly still, perfectly calm, you'd know its energy exactly, and you'd know the moment of that measurement exactly, both at once, and the universe does not allow that. So, if even the void is seething, then what does nothing really mean? The void isn't empty. The vacuum hums, and within that hum lies an energy so subtle, yet so vast, it might be reshaping the cosmos itself, the space between the stars, between the planets, between the atoms in your body. It is not empty. It is singing. In classical physics, a vacuum is the simplest possible thing, a region stripped of all matter, all energy, all motion, nothing. But quantum mechanics doesn't allow perfect stillness. According to the uncertainty principle, You cannot have a field sitting exactly at zero energy for all time. Energy and time are conjugate variables, linked by the same trade-off that binds position and momentum. If the energy of a field were exactly zero, its duration at that state would be infinite, perfectly defined. But nature forbids such certainty. Instead, quantum fields, the invisible entities that fill all of space and give rise to particles when excited, must fluctuate. They tremble. Even in the absence of real particles, they buzz with virtual ones, brief sparks of existence that appear and vanish in the time it takes light to cross a distance smaller than an atom. The vacuum is not a void, it's a sea of Tianzai Neng Liang, a restless fabric that never truly rests. One of the first hints of this came in 1948 from a Dutch physicist named Hendrik Casimir. He imagined placing two uncharged parallel metal plates very close together in a perfect vacuum. There's nothing between them. No air, no particles, no fields classically speaking. And yet Casimir predicted the plates would attract each other. Why? Because the vacuum itself exerts pressure. Quantum field theory says that even empty space is filled with virtual photons, fleeting fluctuations in the electromagnetic field. Outside the plates, all possible wavelengths of these virtual photons can exist. But between the plates, only certain wavelengths fit those whose peaks and troughs align perfectly with the gap. Longer wavelengths are excluded. That means there are slightly fewer vacuum fluctuations between the plates than outside them. The imbalance creates a net force pushing the plates together as if the vacuum itself were squeezing them. The force is tiny, unimaginably small, but it's real, and it has been measured again and again, confirming that even nothing has texture, structure, and energy. Another piece of evidence came in 1947 from an experiment by Willis Lamb. He measured the energy levels of electrons in hydrogen atoms with extraordinary precision and found something unexpected: a slight shift, a tiny deviation from what the equations predicted. The electron's orbit was being nudged ever so slightly by the flickering vacuum around it. The empty space wasn't empty. It was interfering subtly, but measurably with the electron's motion. This Lamb shift became one of the earliest direct confirmations that the quantum vacuum is an active participant in the universe, not a passive backdrop. Perhaps the most dramatic consequence of vacuum energy comes from black holes. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Near the event horizon, the boundary beyond which nothing can escape virtual particle pairs can be torn apart by the intense gravity. One particle falls in, the other escapes. To an outside observer, it looks as though the black hole is emitting radiation, glowing faintly with thermal energy. This Hawking radiation is real, and over unimaginable stretches of time, trillions upon trillions of years, it causes black holes to evaporate, losing mass until they vanish entirely in a final burst of energy. A black hole, the most permanent seeming object in the universe, is not eternal. It is slowly dismantled by the vacuum's quantum hum. And then there's dark energy, the mysterious force driving the accelerated expansion of the universe. Observations show that space itself is stretching faster and faster, as though pushed outward by some invisible pressure. The leading explanation is vacuum energy, the cumulative effect of all those quantum fluctuations adding up to a faint but persistent repulsion. 70% of the universe, by energy content, may simply be the weight of empty space. But here's the puzzle. When physicists calculate how much vacuum energy there should be based on quantum field theory, they get a number that's catastrophically large. So large that the universe should have torn itself apart in the first instant of its existence. Yet the actual observed value is tiny, smaller than the prediction by a factor of 10 to the power of 120. This is called the cosmological constant problem, and it remains one of the greatest unsolved mysteries in physics. Somehow, almost all of the vacuum's energy cancels out, leaving behind just a whisper. If the cancellation were even slightly imperfect, if the number were off by just a little, the universe as we know it could not exist. We live, it seems, on the edge of a knife. The vacuum is powerful enough to shape galaxies, yet balanced with such precision that stars can form, planets can cool, and life can emerge. One small shift, one miscalculation in nature's books, and everything collapses or explodes. So the world you're sitting in is not solid, light is not honest, and the space between everything is not empty. It hums with invisible energy, a quiet song that holds the cosmos together. But there is one more secret, stranger still, a secret about connection. You've learned that matter is mostly empty, that light deceives, that the vacuum hums. But the deepest mystery of quantum mechanics isn't about particles or waves. It's about something far more unsettling, the fact that separation itself may be an illusion. There are two particles, separated by 1,000,000 light years. You touch one, the other knows instantly. This is not science fiction. It's not speculation. It's one of the most thoroughly tested, most stubbornly confirmed phenomena in all of quantum physics, and it suggests something profound and disturbing about the nature of reality. That distance at the deepest level doesn't mean what we think it means. That two things once connected may never truly separate. That the universe is woven together by invisible threads that stretch across space and time, binding everything into a single, inseparable whole. This effect is called entanglement, and Albert Einstein hated it. He called it spooky action at a distance, a phrase that captured both his skepticism and his unease. To understand why, imagine a simple story. A pair of gloves. You have a left glove and a right glove. You place each glove in a separate box, seal them, and send one box to Mars. When you open the box on Earth and find the left glove, you instantly know the other box contains the right glove. Simple, obvious. The information was there all along, hidden but determined. You just didn't know it yet. Quantum entanglement is nothing like that. In the quantum version, before you open either box, neither glove is left or right. Both gloves exist in a superposition, a blend of both possibilities. The moment you open one box and observe a left glove, the other glove, no matter how far away, instantaneously becomes the right glove. Not because it was always the right glove, but because the act of measuring one forces the entire system to collapse into a single, correlated outcome. The two particles don't carry hidden instructions. They don't secretly know what they'll be when measured. They are genuinely undecided, connected by a shared quantum state. And the measurement of one determines the state of the other, faster than light could ever travel between them. Einstein saw this as proof that quantum mechanics was incomplete. In 1935, he and two colleagues, Boris Podolsky and Nathan Rosen, published a paper now known as the EPR paradox. They argued that if quantum mechanics allowed such instantaneous correlations, then either information was traveling faster than light-violating relativity, or there were hidden variables, unknown factors, that predetermined the outcomes in ways quantum mechanics couldn't see. Either way, they concluded the theory was missing something. For decades, the argument remained philosophical, interesting, but untestable. Then in 1964, an Irish physicist named John Bell changed everything. He derived a set of mathematical inequalities, precise limits on how strong correlations could be if hidden variables were responsible. If experiments could produce correlations stronger than Bell's limits, it would mean no local hidden variable theory could explain them. The universe would have to be fundamentally non-local, allowing connections that transcend space. The experiments began in the 1970s and reached their peak in the 1980s with the work of French physicist Alain Aspect. He and his team created pairs of entangled photons, sent them in opposite directions, and measured their polarizations. The correlations they found were stronger than Bell's inequalities allowed, significantly stronger. The results have been repeated thousands of times since, with ever more stringent controls, closing every conceivable loophole. Every test confirms the same unsettling truth. Quantum mechanics is right. The universe is non-local. Entangled particles share information in ways that cannot be explained by anything traveling between them. And yet this connection cannot be used to send messages. The results of measurements on entangled particles are still random. You can't control which outcome you get. So even though the particles are correlated, no signal, no usable information passes faster than light. It's as if two dice rolled on opposite sides of the galaxy always add up to 7. Each roll is unpredictable. But when you compare them later, the pattern is perfect. The universe enforces the correlation without transmitting anything. Einstein was wrong, but his instinct was understandable. Entanglement feels impossible. It suggests that space, for all its vastness, is not a barrier. That particles once connected remain part of a single system no matter how far they drift apart. It's not that they communicate across the distance. It's that the distance, in some strange quantum sense, doesn't fully separate them. In 2017, scientists demonstrated entanglement between a ground station on Earth and a satellite orbiting in space more than 1,000 kilometers away. Photons entangled on the ground were sent up through the atmosphere, surviving turbulence and noise, their correlations intact. The experiment proved that entanglement can endure across vast distances under real-world conditions, opening the door to technologies that were once pure fantasy. One of those technologies is quantum communication. Traditional encryption relies on the difficulty of certain mathematical problems. Break the math, break the code. But quantum key distribution uses entangled particles to generate encryption keys. If anyone tries to intercept the key, they must measure the particles. And measurement, as we've learned, disturbs the system. The eavesdropper's presence is immediately detected. The security isn't based on complexity. It's based on the laws of physics. unbreakable in principle because nature itself guards the information. Another application is quantum teleportation. The name is misleading. You're not beaming matter across space like in science fiction, but you can transfer the quantum state of one particle to another distant particle using entanglement and classical communication. The original state is destroyed in the process, as required by the no-cloning theorem, but the information is perfectly reconstructed elsewhere. Scientists have teleported the states of photons, atoms, even small clusters of particles over distances of hundreds of kilometers. It's not faster than light travel, but it's a way of moving quantum information without physically carrying it. Entanglement also plays a role in the natural world, though we're only beginning to understand how. Some researchers believe it helps plants perform photosynthesis with near-perfect efficiency, allowing energy to find the optimal path through molecular networks by exploring multiple routes simultaneously. It may be involved in bird navigation in the way certain species sense Earth's magnetic field. Even the fabric of space-time itself, according to some theories, might be stitched together by entanglement, a kind of quantum glue, holding the geometry of the universe in place. What's most remarkable is how ordinary entanglement has become in the lab. It's no longer a curiosity, it's a tool. Physicists entangle particles routinely, not as a novelty, but as a resource for computation, communication, and sensing. The strangeness hasn't gone away, but it's been domesticated, harnessed, woven into the machinery of emerging technologies. Still, the philosophical weight remains. Entanglement tells us that the universe is not a collection of separate objects bumping into each other in empty space. It's a web, a network of relationships where every particle, every atom, every quantum system is connected to everything it has ever interacted with. The boundaries we see, the distances we measure, are real in one sense, but in another deeper sense, they're illusions. The universe is one thing expressing itself as many. So, if two particles can remain connected across 1,000,000 light years, are you truly separate from the world around you? Entanglement shows that connection transcends space, but there's another kind of connection hidden inside every particle, an invisible compass that shapes everything from magnets to minds. Every particle in the universe carries an invisible compass, but this compass doesn't just point in two directions, and it's not really spinning at all. This property is called spin, and it's one of the strangest, most fundamental features of quantum mechanics. The name is misleading. When we say an electron has spin, we don't mean it's rotating like a tiny planet. If it were the surface, would have to be moving faster than the speed of light, which is impossible. Spin is intrinsic, built-in, a kind of angular momentum that exists without motion, a quality that simply is like charge or mass. Every electron in the universe has the same spin, every photon, every quark. It's one of nature's fingerprints stamped into the identity of each particle. The discovery of spin came in the early 1920s when physicists noticed something odd about the light emitted by atoms. According to the models of the time, certain atomic transitions should produce single, sharp lines of color. But when examined closely, those lines split into pairs, doublets, as if the electron had an extra degree of freedom, an extra way to differ from itself. In 1925, two young Dutch physicists, George Uhlenbeck and Samuel Goudsmit, proposed a bold solution. The electron, they suggested, carries an intrinsic angular momentum, a quantum spin of 1/2. That extra twist explained the splitting perfectly. But spin 1/2 is bizarre. In classical physics, angular momentum is continuous. An object can spin at any rate. Faster, slower, stopped entirely. In quantum mechanics, spin comes in discrete units. Electrons, protons, and neutrons all have spin 1/2. Photons and gluons have spin 1. The Higgs boson has spin 0. These aren't arbitrary labels. They determine how particles behave, how they interact, and which family they belong to. Particles with half integer spin like 1/2 or 3/2 are called fermions. Particles with integer spin like 0 or 1 are called bosons. This division is not a detail. It's foundational. It shapes the structure of matter, the nature of forces, and the stability of the universe. Spin also obeys a strange symmetry rule. If you rotate an ordinary object by 360 degrees, it looks the same. One full turn brings you back to the start. But rotate an electron's quantum state by 360 degrees, and it doesn't return to its original form. It picks up a minus sign, a phase shift, only after a full 720 degrees, 2 complete rotations, does it truly come back to itself. The universe somehow keeps track of how many times you've turned something, even if you can't see the difference. It's written into the mathematics, and it's been confirmed in countless experiments. One of the most elegant demonstrations of spin came in 1922, before the concept was even fully understood. Otto Stern and Walter Gerlach fired a beam of silver atoms through a non-uniform magnetic field. Classical physics predicted that the atom's magnetic moments would be randomly oriented, producing a continuous smear on the detector. Instead, the beam split cleanly into 2 spots, up and down. The silver atoms, each containing a single, unpaired electron, had only 2 possible orientations of spin, nothing in between. It was one of the first direct pieces of evidence that quantum mechanics doesn't allow smooth, continuous values. Everything comes in steps. This 2-state nature of spin makes it ideal for storing information. In fact, modern quantum computers often use the spin of electrons, atomic nuclei, or photons as qubits. A classical bit is either 0 or 1. A spin qubit can be both up and down, simultaneously existing in superposition until measured. By entangling multiple spins, quantum computers can explore vast landscapes of possibility in parallel, performing calculations that would take classical machines longer than the age of the universe. But spin isn't just abstract. It has tangible effects. Every electron, because of its spin, acts like a tiny bar magnet. In most materials, these magnetic moments point in random directions, canceling each other out. But in ferromagnetic substances, like iron, cobalt, and nickel, the spins of countless electrons align in the same direction through quantum interactions called exchange forces. When large regions of aligned spins form, they create magnetic domains. And when those domains line up, you get a magnet strong enough to hold a note to a refrigerator door. That familiar tug you feel when you stick a magnet to metal is simply quantum spin made visible. Spin also governs chemistry. When 2 electrons occupy the same orbital in an atom, they must have opposite spins. This is a direct consequence of the Pauli exclusion principle, which arises from the fact that electrons are fermions. No two fermions can share the same quantum state. That rule, simple as it sounds, is why atoms have structure, why matter has volume, and why the periodic table exists in its layered form. Without spin, electrons would collapse into the lowest energy level, and all of chemistry would vanish. Even the light that reaches your eyes is shaped by spin. Photons, the carriers of electromagnetic radiation, have spin 1, but unlike electrons, their spin aligns with their direction of motion, producing what we call polarization. When you wear polarized sunglasses, you're filtering light based on its spin orientation. The glare from water or glass, the shimmer on a wet road, it all disappears because your lenses only allow photons of a certain polarization to pass through. Every time you tilt your head and watch the light change, you're interacting with quantum spin at a macroscopic scale. In particle physics, spin acts as a cosmic classifier. It determines not only what a particle is, but also how it behaves. Fermions with half-integer spin build up the material world by stacking in complex ways. Bosons with integer spin mediate forces, allowing fermions to communicate their presence. The photon's spin 1 makes electromagnetism work. The gluon's spin 1 binds quarks together inside protons and neutrons. The Higgs boson, discovered in 2012, has spin 0, giving it a unique ability to endow other particles with mass. Even the graviton, if it exists, would have spin 2 corresponding to the fabric of space-time itself. Spin is one of those quantum features that hints at the underlying symmetry of the universe. It's connected to the concept of rotational invariance, the idea that the laws of physics don't change when you rotate your frame of reference. Mathematically, this is captured by something called spinor transformations, which describe how quantum states twist under rotation. Spinors are subtle creatures. They carry the memory of rotation, encoding how particles respond to changes in orientation. They're the reason an electron's wave function needs 2 full turns to come back home. At human scale, spin's effects are invisible, but at quantum scales, they dominate everything. In medical imaging, magnetic resonance, imaging MRI machines exploit the spins of atomic nuclei by aligning them in a magnetic field and then flipping them with radio pulses. As the spins relax back into alignment, they release radio waves that reveal the intricate architecture of the human body. Each bright pixel in those images comes from nuclei relaxing, releasing their spin energy. The same physics behind a simple magnet powers one of medicine's most important tools. Spin also underpins phenomena like superconductivity, where electrons form pairs with opposite spins, so-called Cooper pairs that move through materials without resistance. It's even central to the field of spintronics, where information is stored and transmitted through spin orientation rather than electric charge. Devices based on spintronics could one day outperform traditional electronics in speed and energy efficiency. So, while the word spin might suggest something familiar, what it really represents is one of the universe's most fundamental forms of order. It's a hidden quantum compass inside every particle, guiding its behavior, dictating its interactions, and giving rise to nearly every magnetic and structural feature of matter. But spin is just one piece of a larger puzzle, because at the deepest level, particles themselves may not be particles at all. Spin divides the universe into two families, and the difference between them shapes everything from the air you breathe to the stars that burn above you. Imagine starting an electric current in a loop of wire. Now, imagine that current flowing forever, not for years, not for centuries, forever. No battery, no power source, no loss of energy, just motion perpetual and perfect, as if friction itself had been erased from the laws of physics. This is not a thought experiment, it's real, and it's called superconductivity. In 1911, a Dutch physicist named Heike Kamerlingh Onnes was experimenting with materials cooled to temperatures near absolute zero. He had just succeeded in liquefying helium, reaching the coldest temperatures ever achieved in a laboratory. Curious about how metals behaved in such extreme cold, he took a sample of mercury and chilled it down to around 4 degrees above absolute zero. What happened next was astonishing. The electrical resistance of the mercury didn't just decrease, it vanished completely. The metal conducted electricity with perfect efficiency, as if the electrons encountered no obstacles at all. If you start a current flowing in a superconducting loop, it will continue circulating indefinitely. Experiments have confirmed currents lasting for years with no measurable decay. In principle, they could flow for the lifetime of the universe. The energy doesn't drain away, it simply persists, locked in motion, a kind of perpetual glide that defies everything we know about friction and entropy. For decades, no one understood how this was possible. In a normal metal, electrons constantly collide with vibrating atoms in the crystal lattice, losing energy as heat. That's resistance. But in a superconductor, those collisions somehow stop. The electrons move in perfect harmony, undisturbed, as if the material itself had become frictionless. The breakthrough came in 1957 when 3 American physicists, John Bardeen, Leon Cooper, and Robert Schrieffer, developed what is now known as BCS theory. They realized that under the right conditions, electrons can form pairs, now called Cooper pairs. Normally, electrons repel each other because they both carry negative charge, but at extremely low temperatures, they can attract weakly through interactions with the vibrating lattice of atoms around them. One electron distorts the lattice slightly as it passes, creating a region of positive charge that attracts a second electron. The two become bound, not tightly, but just enough to act as a single unit. And here's the key. A Cooper pair made of 2 spin 1/2 electrons behaves like a boson, a particle with integer spin. Bosons don't obey the Pauli exclusion principle. They can all occupy the same quantum state, moving together in perfect synchrony. When billions upon billions of Cooper pairs condense into the same state, they form a single, coherent quantum wave that extends across the entire material. This macroscopic wave cannot be easily disrupted. Individual collisions with atoms no longer matter because the pairs move as one collective entity. Resistance disappears. But superconductivity does more than eliminate resistance. It also expels magnetic fields. This effect, discovered in 1933 by Walter Meissner and Robert Oxenfeld, is now called the Meissner effect. When a material becomes superconducting, it doesn't just allow magnetic fields to pass through unimpeded. It actively pushes them out. Place a magnet near a superconducting surface, and the magnet will levitate, held up by the repulsion of its own magnetic field which the superconductor refuses to let inside. This isn't just magnetic repulsion in the ordinary sense. It's a fundamental reorganization of the material's quantum state. The superconductor becomes diamagnetic to an extreme degree, generating currents on its surface that precisely cancel any external magnetic field trying to penetrate. The result is perfect levitation, stable and frictionless. Maglev trains which float above their tracks using superconducting magnets are a direct application of this principle. Superconductivity also gave rise to one of the most astonishing quantum effects ever discovered, the Josephson effect. In 1962, a young British physicist named Brian Josephson predicted that if two superconductors were separated by a very thin insulating barrier, just a few atoms thick, Cooper pairs could tunnel through the barrier without any applied voltage. This was quantum tunneling. On a macroscopic scale, electrons passing effortlessly through a wall that should have been impenetrable. Even more remarkably, if a small voltage were applied across the junction, the current would oscillate at a frequency precisely determined by that voltage. The relationship is so exact, so universal, that it depends only on fundamental constants. The charge of the electron, Planck's constant, nothing else. When Josephson's prediction was confirmed experimentally, it opened an entirely new field of technology. A Josephson junction, the sandwich of two superconductors with a thin insulator between, became the cornerstone of ultra-sensitive devices known as SQUIDs, superconducting quantum interference devices. A SQUID exploits the fact that superconducting currents are governed by a quantum phase, a hidden variable that can interfere with itself, much like light waves in a double-slit experiment. When magnetic flux passes through a superconducting loop containing Josephson junctions, it shifts the phase of the current ever so slightly. By measuring those shifts, a SQUID can detect magnetic fields as faint as 1 part in a trillion of Earth's own magnetic field. These devices are sensitive enough to measure the magnetic activity of the human brain, detecting the faint signals produced by firing neurons. They can find flaws deep inside materials, map underground mineral deposits, and even pick up the magnetic signature of a single quantum event. The precision of the Josephson effect goes beyond measurement. Because the frequency of the oscillating current depends only on fundamental constants, it serves as a natural voltage standard. National laboratories around the world use Josephson junctions to define the volt with astonishing accuracy, linking electrical units directly to the bedrock of quantum mechanics. Superconductivity also provides a glimpse into how deeply quantum mechanics can shape macroscopic matter. The current flowing through a superconducting loop isn't a random swarm of electrons. It's a single quantum wave wrapping around itself. This means it can interfere, oscillate, and even exist in superpositions, just like a photon or an atom. In the past 2 decades, scientists have learned to harness these properties to build one of the most promising architectures for quantum computing. In a superconducting quantum computer, tiny circuits made of Josephson junctions act as qubits. Each qubit can represent both 0 and 1 simultaneously encoded in the direction of a current circulating around a loop. Because these circuits are macroscopic, visible under a microscope, they allow engineers to build quantum systems large enough to manipulate directly. Yet because they are superconducting, they behave as pure quantum objects capable of entanglement, superposition, and interference. By coupling many such qubits together, researchers can perform calculations that in principle no classical computer could match. The challenge, of course, is coherence. Superconductors are remarkably robust against some kinds of noise, but even the tiniest interaction with the outside world can disturb their delicate quantum states. That's why these circuits are cooled to temperatures just a few thousandths of a degree above absolute zero, housed in elaborate refrigerators that resemble gleaming silver chandeliers. Inside those frigid chambers, electrons pair up and glide through their crystalline playgrounds in unison, their quantum choreography unfolding in perfect silence. Beyond computing, superconductivity has already transformed technology in countless ways. MRI machines use powerful superconducting magnets to peer inside the human body. Particle accelerators rely on them to steer and focus beams traveling near the speed of light. Maglev trains float effortlessly above their tracks, supported by superconducting magnets repelling the rails below. In all these cases, the effect that began as a laboratory curiosity in 1911 has become an indispensable tool of modern science and engineering. And yet, despite a century of progress, superconductivity still holds mysteries. Researchers continue to hunt for materials that can become superconducting at higher temperatures, ideally at room temperature. In recent years, compounds of hydrogen and rare metals have shown tantalizing results, becoming superconducting under immense pressures. If the phenomenon could ever be achieved in everyday conditions, the impact would be revolutionary. Lossless power grids, perfectly efficient motors, electronics without waste heat. At its core, superconductivity is a story about cooperation. It's what happens when countless electrons, which normally repel one another, fall into alignment and act as one. It's nature showing that when individual particles give up their independence and move together in perfect phase, resistance vanishes. And in that stillness where friction disappears and waves move as one, we glimpse a rare kind of perfection, the universe finally, without loss. Superconductivity shows what happens when particles synchronize perfectly. But there's an even stranger state of matter, one where atoms themselves lose their identity and merge into a single quantum entity. Imagine cooling a cloud of gas, not just cold, not merely frozen, but colder than anything that exists naturally anywhere in the universe, colder than the vacuum of space, colder than the faint glow left over from the Big Bang, so cold that you're just a whisper away from absolute zero, the point where all motion should cease, where even atoms should fall silent. And then, at that unimaginable threshold, something extraordinary happens. The atoms stop being individual. They don't disappear. They don't clump together like ice crystals. They do something far stranger. They blur. They overlap. Their quantum wave functions, which normally describe where each atom might be found, begin to merge and intertwine until you can no longer tell one atom from another. The entire cloud collapses into a single unified quantum state. Billions of atoms acting as one. A single giant wave visible to the naked eye. This is the Bose-Einstein condensate, and it's one of the most alien states of matter ever created. The idea was first predicted in 1924 by Indian physicist Satyendra Nath Bose and Albert Einstein. They realized through pure mathematics that if you cooled a gas of bosonic atoms to temperatures near absolute zero, something remarkable should happen. The particles would lose their thermal energy, their random jostling, and settle into the lowest possible energy state. Not just a few of them, all of them, at once. But for 70 years, it remained a theory, a beautiful mathematical curiosity with no experimental proof. The temperatures required were simply too extreme. Then in 1995, physicists at the University of Colorado and MIT succeeded. Using lasers to slow atoms and magnetic fields to trap them, they cooled a cloud of rubidium atoms to about 0.0001 degrees above absolute zero. And there it was, the condensate, a drop of quantum matter hovering in mid-air, glowing faintly in the instruments. The achievement earned the Nobel Prize in 2001, and it opened a door into a world where quantum mechanics, usually invisible, becomes something you can almost touch. In a normal gas, every atom has its own identity, its own position, its own momentum, its own wave function. They move independently, colliding and bouncing like billiard balls in slow motion. But in a Bose-Einstein condensate, that independence vanishes. The wave functions of all the atoms overlap so completely that they form a single macroscopic quantum wave, a coherent entity that behaves not like a collection of particles, but like one enormous superatom. And here's the astonishing part. You can see it. Normally, the de Broglie wavelength of an atom, the quantum wave that describes its position and momentum, is incredibly tiny, far too small to detect directly. But in a condensate, that wavelength stretches out, extending across millimeters, millions of times larger than the atom itself. When scientists shine light through a Bose-Einstein condensate and capture the shadow it casts, they see interference patterns, the telltale ripples of quantum waves overlapping and canceling. It's quantum mechanics made visible, a glow of probability frozen in time framed in a photograph. For the first time in history, the abstract mathematics of wave functions became something tangible, something you could point to and say, there, that's quantum coherence, that's superposition, that's the wave nature of matter, no longer hidden behind the noise of temperature and motion, but laid bare for anyone to see. But Bose-Einstein condensates aren't the only quantum fluids that defy intuition. There's another one that's been known for much longer, and it's just as strange. Superfluid helium. Helium is already an unusual element. It's so light, so reluctant to bond with anything that it stays a gas even at temperatures where everything else has frozen solid. But cool helium-4, a bosonic isotope, below 2.17 Kelvin, and something astonishing happens. The liquid helium suddenly loses all viscosity. Completely. It becomes a superfluid, a substance that flows without friction, without resistance, without any of the properties we associate with ordinary liquids. Pour superfluid helium into a container, and it will climb the walls, not slowly, like water creeping up paper through capillary action, but smoothly, steadily, as if gravity means nothing to it. The liquid forms a thin film on the inside of the container, flows up and over the edge, and drips down the outside, emptying itself like a ghost escaping a trap. Spin a container of superfluid helium, And it doesn't rotate like water in a bucket. Instead, it forms an array of tiny, quantized vortices, miniature whirlpools, each carrying exactly 1 unit of angular momentum. No more, no less. You can't make a vortex half that size. You can't make one twice as large. The vortices are discrete, countable, like particles of rotation. It's as if the liquid itself obeys quantum rules, normally reserved for single atoms. The reason is the same as for Bose-Einstein condensates. Below a critical temperature, the helium atoms fall into the same quantum state, forming a single coherent wave that extends across the entire fluid. Individual collisions no longer matter. The atoms move as one, and that collective motion cannot be easily disrupted. Friction, which arises from countless microscopic interactions, simply vanishes. Scientists have even passed superfluid helium through holes so tiny that ordinary liquids couldn't squeeze through. The superfluid flows effortlessly, as if the barrier weren't there. It seeps through cracks that should be impossible to penetrate, not because it's forcing its way, but because its quantum wave function simply exists on both sides simultaneously. This is quantum mechanics on a scale you can pour into a cup. But not all particles can do this. Not all particles are bosons. Fermions particles, like electrons, protons, and neutrons, play by different rules. They can't all pile into the same state. The Pauli exclusion principle forbids it. Even at absolute zero, where all thermal motion stops, fermions must stack up layer by layer, each occupying a unique quantum state. Like students filling seats in an auditorium, the lowest seats fill first, then the next row, then the next, until every available spot is taken. This stacking creates what physicists call a Fermi sea, a kind of quantum ocean, where each particle occupies a distinct level. The highest occupied level is called the Fermi surface, and it determines much of how the material behaves. In metals, for instance, the electrons form a Fermi sea that dictates how electricity flows and how heat conducts. Only the electrons near the Fermi surface, the ones with just enough energy to move, contribute to electrical current. The rest are locked in place, unable to shift, because there's no empty state for them to move into. The Fermi sea isn't just a curiosity of condensed matter physics. It governs the structure of matter throughout the universe. Inside white dwarf stars, the burnt-out cores of dead suns, electrons are packed so densely that the Pauli exclusion principle creates an immense pressure, a quantum force pushing outward against gravity. This is degeneracy pressure, and it's purely quantum mechanical. There's no heat involved, no thermal motion, just the fact that fermions refuse to share the same state, even under the crushing weight of a collapsing star. That refusal is strong enough to hold up a white dwarf, an object with the mass of the sun compressed into something the size of Earth. Without degeneracy pressure, without the exclusion principle, the star would collapse instantly into a black hole. It's quantum mechanics, not heat or gas pressure, that keeps the remnants of stars from vanishing into oblivion. And it's not just electrons. In neutron stars, where gravity is so strong that even atoms are crushed, the neutrons themselves form a Fermi sea, packed together so tightly that they still resist further compression, generating a pressure so intense it can support a star denser than an atomic nucleus. A teaspoon of neutron star material would weigh 1 billion tons, and the only reason it doesn't collapse into a singularity is because the neutrons, like stubborn children, refuse to occupy the same quantum seat. So here's the pattern. Bosons create harmony. When cooled to near absolute zero, they fall into the same state, moving together, singing the same note. Fermions create structure. They resist, they stack. They build layers of order by refusing to overlap. One creates coherence, the other creates stability. And together they shape everything from the flow of superfluids to the death of stars. But beneath both families, beneath the harmony and the structure, lies something even deeper, a principle so fundamental that it doesn't just describe particles, it describes the very fabric of reality itself. Bosons harmonize, fermions organize. But what if particles themselves are not the fundamental truth? What if beneath every atom, every photon, every quantum of spin, there's something more elemental, not objects moving through space, but space itself vibrating? You are not a collection of atoms. You are a melody, a pattern of vibrations rippling through an invisible sea. This is not poetry. It's physics, modern physics, the deepest description of reality we have. And it tells us something astonishing. There are no particles. Not really. Not in the way you imagine them. No tiny billiard balls bouncing through space. No solid, indivisible specks of matter. Instead, there are fields, invisible, intangible fields that fill every point in the universe, stretching from here to the edge of the cosmos and beyond. And what we call particles, electrons, photons, quarks are not things. They're disturbances in those fields, ripples, waves, notes in a cosmic symphony. This is quantum field theory, and it's the language in which the universe is written. Imagine an infinite ocean perfectly still, stretching in every direction. Now imagine dropping a stone. A ripple spreads outward, a localized disturbance, carrying energy across the water. That ripple is not made of anything separate from the water. It is the water moving, vibrating temporarily, concentrated in one place. The ripple has properties, a wavelength, an amplitude, a speed, but it's not a thing in itself. It's an event, a pattern. Particles are like that. An electron is not a tiny ball of negative charge. It's a ripple in the electron field, an invisible entity that exists everywhere in space, even where no electrons are detected. When enough energy concentrates in one spot, the field vibrates, and that vibration is what we call an electron. Its mass, its charge, its spin, all of those properties come from the way the field oscillates. The particle is the note, the field is the instrument, and every electron in the universe is a note played on the same instrument. That's why all electrons are identical, not similar, not nearly the same, but perfectly, absolutely identical. There's no such thing as a different electron. There's no serial number, no individual history that marks one as distinct from another. They're all excitations of the same underlying field, and the field doesn't care where or when the excitation happens. Every electron is the same because there is only one electron field humming quietly, everywhere waiting to be plucked. The same is true for photons. There's a photon field, also called the electromagnetic field, that fills all of space. When you turn on a light, you're not creating photons out of nothing. You're exciting the electromagnetic field, causing it to vibrate. Those vibrations propagate outward as light, and when they strike your eye, they excite the electron field in your retina, triggering a cascade of chemical reactions that your brain interprets as vision. Light doesn't travel through space. It is space briefly animated. Even forces, the pushes and pulls we feel are just fields talking to each other. When two electrons repel, it's tempting to imagine them as little magnets pushing apart. But that's not what's happening. What's actually happening is the electron field around one electron disturbs the electromagnetic field. That disturbance propagates outward as a virtual photon, a temporary ripple in the photon field that never quite becomes real enough to detect. The virtual photon reaches the second electron and transfers momentum, nudging the electron field there. The result? The electrons move apart, not because they touched, not because an invisible hand pushed them, but because the fields exchanged information, one vibration influencing another. Forces in quantum field theory are not pulls or pushes. They're conversations between fields, and there's one field unlike any other, the Higgs field, named after physicist Peter Higgs, who predicted it in the 1960s. The Higgs field is what gives particles mass. Before the Higgs field was discovered, this was one of the great mysteries of physics. Why do some particles have mass and others don't? Why is an electron light and a top quark heavy? What does mass even mean? The answer is resistance. The Higgs field fills all of space, a kind of invisible molasses that particles must move through. Some particles, like photons, don't interact with the Higgs field at all. They glide through it effortlessly, which is why light always travels at the speed of light. It has no mass to slow it down. Other particles, like electrons and quarks, interact strongly with the Higgs field. As they move, the field resists, clinging to them, dragging on them, giving them inertia. That resistance is what we experience as mass. The more strongly a particle interacts with the Higgs field, the heavier it is. The top quark, the heaviest known fundamental particle, is like a boulder trying to wade through honey. The electron, much lighter, is like a pebble skipping across water. And the photon, massless, doesn't touch the honey at all. Without the Higgs field, there would be no mass. Without mass, atoms couldn't form. Electrons would fly away at the speed of light. Protons and neutrons couldn't bind together. Chemistry would be impossible. Stars wouldn't ignite. Galaxies wouldn't form. There would be no structure, no complexity, no life. The Higgs field is the reason the universe isn't just a formless soup of massless particles zipping around forever. So, the universe is not made of stuff. It's made of fields. And those fields, all of them, are cataloged in what physicists call the Standard Model. The Standard Model is a list, a roster of the fundamental fields that, as far as we can tell, make up everything. There are 6 quark fields, up, down, charm, strange, top, and bottom. There are 6 lepton fields, the electron, the muon, the tau, and their corresponding neutrinos. There are 4 force-carrying fields, the photon field for electromagnetism, the gluon field for the strong nuclear force, and the W and Z boson fields for the weak nuclear force. And there's the Higgs field, sitting quietly in the background, giving mass to everything that has it. That's it. 17 fields. 17 instruments in the orchestra. Every atom in your body, every star in the sky, every force, every interaction is just these 17 fields vibrating in different combinations. The universe is not infinite in variety. It's a finite symphony played over and over with exquisite variations. And yet we know the standard model is incomplete. There's no field for gravity. Einstein's general relativity describes gravity as the curvature of space-time itself, but it doesn't fit neatly into the quantum framework. Physicists have long suspected that gravity, too, must be a field carried by a hypothetical particle called the graviton with a spin of 2, but the graviton has never been detected. The mathematics of quantum gravity remains elusive, fractured, incomplete. Then there's dark matter, the invisible substance that makes up 85% of the matter in the universe. We know it's there because we see its gravitational effects, bending light, holding galaxies together, shaping the large-scale structure of the cosmos. But we don't know what it is. It doesn't interact with light. It doesn't emit, absorb, or reflect photons. It's a field we haven't identified, yet a note in the symphony we can't quite hear. And there's dark energy, the mysterious force accelerating the universe's expansion. Is it a property of space-time itself, a new field we've never encountered, or something even stranger we don't know? The standard model is beautiful, elegant, precise. It predicts the behavior of particles to 1 part in a trillion. But it's not the final answer. It's a map, not the territory. And the map has blank spaces, regions we've glimpsed but not yet explored. Still, what we do know is profound. Every object you see, every sensation you feel, every force you experience is the result of fields vibrating in harmony. You are not a solid thing. You are a pattern, a temporary arrangement of ripples in the electron field, the quark field, the Higgs field, all moving together, all singing the same song. When you move your hand, you're not pushing atoms through space. You're shifting the intensity of fields, changing the amplitude of vibrations, conducting a tiny orchestra that for a brief moment has a name and a heartbeat. And when you die, the fields don't disappear. They never do. They simply stop vibrating in the specific pattern that was you. The energy redistributes. The waves flatten. The melody fades. But the fields remain waiting, ready to vibrate again, in new forms, new patterns, new songs. So the universe is not a pile of rocks. It's not a collection of objects. It's a symphony, a single unified composition played on 17 invisible strings stretching across all of space and time. Every particle is a note. Every force is a chord. Every atom is a phrase in a melody so vast, so intricate, that we've only just begun to hear it. But here's the question that haunts every physicist who stares into this truth. If the universe is a symphony, who is the conductor? Or is it us? The fields are real. The vibrations are real. But there's one more mystery left. A mystery not about particles or waves or forces, but about you, about the observer, about whether the universe needs someone to listen before the music begins. The universe is a symphony of fields, but a symphony needs an audience. And that raises the most unsettling question of all. Does reality exist? When no one is looking, if a tree falls in a forest and no one is there to hear it, does it make a sound? It's an old philosophical riddle, the kind that feels clever at parties, but meaningless in the real world. Of course, the tree makes a sound. Sound is just vibrating air. The air vibrates whether you're there or not. The question seems trivial, a word game, nothing more. But quantum mechanics says no. The tree doesn't fall, not until you look. This is not metaphor. It's not exaggeration. It's the strangest, most philosophically unsettling aspect of quantum physics. And after a century of experiments, after thousands of tests designed to catch the universe in a lie, the conclusion remains the same. Measurement changes reality. Observation matters. And no one, not even the greatest minds in physics, fully agrees on what that means. Let's start with what we know for certain. Before you measure a quantum system, it exists in a superposition, a blend of all possible outcomes, each weighted by probability. The electron isn't here or there. It's both simultaneously described by a wave function that stretches across space like a cloud of maybe. The photon isn't polarized vertically or horizontally. It's a mixture of both, humming with indecision. This isn't ignorance. This isn't a lack of information. The particle genuinely doesn't have a definite state. The possibilities coexist, interfering with each other, creating the ripples and fringes we see in double-slit experiments. But the moment you measure it, something changes. The wave function collapses. The cloud of possibilities shrinks to a single point. The electron appears here, not there. The photon chooses vertical, not horizontal. One outcome becomes real, and all the others vanish as if they never existed at all. The superposition, that delicate balance of what could be, dissolves into the hard certainty of what is. And this collapse, this sudden snap from many to one, happens because of measurement, because something, a detector, photon of light, even a stray molecule of air, interacted with the system. The question that has haunted physicists for 100 years is this: what counts as a measurement, and what exactly causes the collapse? In the early days of quantum mechanics, Niels Bohr and Werner Heisenberg, working in Copenhagen, proposed what became known as the Copenhagen interpretation. It's the most famous, most taught, and perhaps most frustrating answer to the measurement problem. According to Bohr, quantum mechanics doesn't describe an objective reality that exists independently of observation. It describes the outcomes of measurements, the interface between the observer and the observed. The wave function in this view isn't a real physical wave rippling through space. It's a mathematical tool, a catalog of probabilities, a way of encoding what we can know. When you perform a measurement, you force the system to reveal one of its possibilities. The wave function collapses to reflect that result. But asking what the particle was doing before the measurement, what state it really had, is meaningless. Quantum mechanics only tells you what you can say about nature, not what nature is when you're not looking. Bohr was pragmatic, almost defiant in his modesty. He argued that the job of physics is to predict experimental outcomes, not to peer behind the curtain and describe some hidden reality. If the equations work, if they predict what we see, that's enough. Anything beyond that is philosophy, not science. But not everyone was satisfied. Albert Einstein famously despised this interpretation. To him, the idea that reality depended on observation felt absurd, even insulting. Do you really believe the moon isn't there when you're not looking at it? He once asked a colleague. To Einstein, quantum mechanics, for all its success, must be incomplete. There had to be something deeper, some hidden layer of reality variables. We couldn't yet see that determined outcomes in advance. The randomness, the collapse, the dependence on measurement, all of it was just a sign that we hadn't figured out the full picture yet. Einstein's discomfort gave birth to alternative interpretations, each attempting to restore some sense of order, some way to make the quantum world feel less alien. And one of the most radical, most audacious answers came in 1957 from a young physicist named Hugh Everett III. Everett proposed something shocking. What if the wave function never collapses? What if instead all possible outcomes happen? This is the many worlds interpretation, and it's exactly as strange as it sounds. According to Everett, when you measure a quantum system, the universe doesn't choose one outcome over the others. It splits. It branches. Every possible result occurs each in its own separate universe. In one universe, you measure the electron on the left. In another, you measure it on the right. In one universe, Schrödinger's cat is alive. In another, it's dead. Both outcomes are real. Both universes exist. You just can't see the other one because your consciousness, your observation, has become entangled with one specific branch. From your perspective, it looks like collapse. You see one outcome and the rest disappear. But that's an illusion. The other outcomes didn't vanish. They're still there, just as real, just as physical, happening in parallel worlds you can never access. Every quantum measurement spawns new universes, an endless cascade of branching realities, each one splitting further and further into a vast, infinite multiverse. The many worlds interpretation eliminates randomness entirely. The wave function evolves deterministically governed by Schrödinger's equation, smooth and predictable. There's no mysterious collapse, no sudden jump from probability to certainty. What we experience as chance is simply our position within the branching tree. We can only see one path, but all the others are just as real. It's an elegant idea in some ways. It takes the mathematics of quantum mechanics completely seriously, without adding collapse as a separate ad hoc rule. But it comes at a staggering cost. It says that every time a quantum event occurs anywhere in the universe, every atom, every photon, every spin measurement, reality multiplies. There are versions of you reading this who made different choices, versions who never existed, versions who live in worlds so divergent from this one that they're unrecognizable. The number of universes is unimaginably vast, growing exponentially with every passing moment. To some physicists, many worlds is beautiful, a natural consequence of the equations, the simplest way to reconcile quantum mechanics with reality. To others, it's extravagant, absurd, a solution that explains one mystery by invoking an infinity of invisible universes. But there's another interpretation, older and quieter, that takes a completely different approach. It's called pilot wave theory, or the de Broglie-Bohm interpretation, named after Louis de Broglie and David Bohm. In this view, particles always have definite positions. They're not smeared out in superposition. They're real solid, located at specific points in space, just like common sense suggests. But they're guided invisibly by a hidden wave, a pilot wave, that evolves according to the Schrödinger equation. The particle surfs this wave, following a deterministic trajectory that looks random only because we can't see the wave itself. The wave explores all possible paths, interfering with itself, creating the patterns we see in double-slit experiments. But the particle itself only travels along one path, guided by the wave's shape. The uncertainty in quantum mechanics isn't fundamental. It's simply our ignorance of the wave's precise form. Pilot wave theory restores determinism. It gives particles definite properties, whether or not we observe them. The electron really does have a position and a momentum, even when no one is looking. Measurement doesn't create reality. It reveals it. But there's a price. The pilot wave must be non-local. It must stretch across all of space, responding instantaneously to changes anywhere in the system. When you measure one entangled particle, the wave guiding the other particle, even light years away, shifts immediately. The theory preserves realism, the idea that things have definite properties, but sacrifices locality, the idea that influences can only travel at or below the speed of light. Einstein might have hated this even more than he hated Copenhagen. And then there's cubism, short for quantum Bayesianism, which takes the most personal, subjective view of all. According to cubism, the wave function isn't a description of external reality. It's a description of your beliefs, your expectations, your personal state of knowledge about what might happen. Quantum mechanics isn't telling you what the universe is doing. It's telling you how to make rational bets. When you measure something, you're not collapsing the wave function of the universe. You're updating your own beliefs based on new information. The wave function is a tool, a probability calculator, not a physical entity. Reality exists, but quantum mechanics doesn't describe it directly. It only describes your relationship to it. Cubism is radical in its subjectivity. It denies that there's a single universal wave function for the whole universe. Every observer has their own wave function, their own probabilities, and those probabilities are personal, not objective. It's not solipsism, the idea that only you exist. It's closer to perspectivism, the idea that reality is best understood through the lens of individual agents navigating uncertainty. To some, cubism feels liberating, honest a recognition that physics is about what we can predict and experience, not about some God's eye view of absolute truth. To others, it feels like giving up, like retreating into subjectivity, when the goal of science is objectivity. So we have Copenhagen, which says reality doesn't exist until measured. Many worlds, which says all realities exist splitting endlessly. Pilot wave, which says reality always exists, but we can't fully see it. And cubism, which says reality exists, but quantum mechanics only describes our beliefs about it. And here's the astonishing thing. All of these interpretations make the same predictions. Every experiment, every measurement, every outcome, they all agree. You can believe in many worlds, or pilot waves, or Copenhagen, or cubism, and your calculations will be identical. The photons behave the same. The electrons scatter the same. The interference patterns are the same. The mathematics is unified. The meaning is not. This is perhaps the deepest lesson of quantum mechanics. The universe can be described predicted controlled, but it resists being fully understood. We've learned its language fluently, precisely, but we don't know what it's saying. The equations work. The technology built on them transforms civilization. But the story beneath the equations remains open, contested, perhaps forever beyond reach. So does the universe need an observer? Does measurement create reality or merely reveal it? Is there a wave function of the entire cosmos, or only localize pockets of probability collapsing and reforming as systems interact, no one knows. And perhaps in a strange way, that's perfect, because it means the deepest question of all, what is real, is still being asked, still being explored, still inviting us to look closer, think harder, and wonder. The interpretations differ, the predictions do not, but there's something even more fundamental than interpretation. There are limits, boundaries written into the laws of nature, rules that tell us not just what happens, but what can never happen. There are things you cannot do, not because technology isn't advanced enough, not because you lack the tools or the time or the cleverness, but because the universe itself, in its most fundamental laws, says no. These are not suggestions. They're not challenges waiting to be overcome. They're absolute boundaries woven into the fabric of reality, enforced by mathematics so elegant and unyielding that no amount of ingenuity can break them. And far from being frustrating, these limits are what make the quantum world both comprehensible and usable. They're the rules of the game, and once you know them, you can start to play. One of the most surprising limits is the no cloning theorem discovered in 1982. It states simply and unequivocally that you cannot make an exact copy of an unknown quantum state. In the classical world, copying is trivial. You can duplicate a file, a photograph, a strand of DNA. You can photocopy a book clone, a sheep reproduce a painting, down to the brushstroke. But in the quantum world, copying is forbidden. Not difficult, not impractical, impossible. Here's why. To copy a quantum state, you'd need to know exactly what that state is. You'd need to measure it, determine its precise configuration of superposition, its amplitudes, its phases. But measurement, as we've learned, changes the state. The act of determining what you want to copy destroys the original. You can't read the information without altering it. And once it's altered, you can't reproduce what it was. This isn't a limitation of our instruments. It's a law of nature derived directly from the structure of quantum mechanics. The mathematics doesn't allow cloning. The universe says one copy only. At first, this might seem like an annoying restriction, a cosmic inconvenience, but it's actually a gift, because the no cloning theorem is what makes quantum cryptography secure. In traditional encryption, security relies on the difficulty of certain mathematical problems. Factor a large number, break the code. But if someone builds a powerful enough computer or discovers a clever shortcut, the encryption fails. Quantum encryption, however, is different. It doesn't rely on difficulty. It relies on the laws of physics. Here's how it works. Two parties, call them Alice and Bob, want to share a secret encryption key. They use entangled photons, sending one to Alice and one to Bob. The quantum states of these photons encode the key. If an eavesdropper, Eve, tries to intercept the photons and measure them to learn the key, she has a problem. Measurement changes the state. The no cloning theorem prevents her from copying the photons to study them later. She can measure them, but that measurement will disturb the system, introducing errors that Alice and Bob can detect. If the error rate in their shared key is higher than what random noise would produce, they know someone has been listening. They discard that key and try again. The security doesn't depend on Eve being careless or on Alice and Bob being clever. It depends on quantum mechanics itself. The eavesdropper's presence is written into the physics. This is quantum key distribution, and it's already being used in the real world. Banks in China transmit secure keys via satellite. Governments test quantum networks across fiber optic cables. The encryption is in principle unbreakable, guaranteed not by human ingenuity, but by the structure of reality. But the no cloning theorem has another consequence, one that sounds like science fiction, but is entirely real. Quantum teleportation. The name is misleading. You're not beaming matter across space. You're not sending particles faster than light. What you're doing is transferring the quantum state of one particle to another distant particle using entanglement and classical communication. Here's how it works. Alice has a particle whose state she wants to send to Bob. She also has one half of an entangled pair, and Bob has the other half. Alice performs a joint measurement on her particle and her half of the entangled pair. This measurement destroys the original state, as required by the no cloning theorem, but it produces two classical bits of information. Alice sends those bits to Bob through an ordinary channel at the speed of light or slower. Bob uses that information to manipulate his half of the entangled pair, transforming it into an exact replica of Alice's original particle. The quantum state has been teleported, not the particle itself, but the information that defines it. The original is gone. The copy is perfect, and at no point did the quantum information travel through space. It simply reappeared, as if the entanglement were a bridge, a shortcut through the fabric of reality. Quantum teleportation has been demonstrated thousands of times. Photons have been teleported across cities. Atomic states have been teleported across labs. In 2017, Chinese scientists teleported a photon's state from the ground to a satellite orbiting more than 1,000 kilometers above Earth. The process is slow, limited by classical communication, but it's real, and it's a glimpse of what future quantum networks might achieve. But teleportation and cryptography both rely on another deep truth of quantum mechanics: contextuality. In the classical world, objects have definite properties, independent of how you measure them. A ball is either red or blue, whether you look at it or not. A coin has two sides, whether you flip it or check. The properties exist waiting to be revealed. In the quantum world, this isn't true. The result of a measurement can depend on what other measurements you're making at the same time. The outcome isn't predetermined. It's created by the act of observation, shaped by the context of the experiment. This is contextuality, and it was formalized by the Cauchy-Specker theorem in 1967. The theorem proves mathematically that you cannot assign definite values to all possible measurements of a quantum system in advance. There's no hidden spreadsheet, no cosmic database where the universe stores the true values of every observable. The values don't exist until you measure them, and which values emerge depends on how you choose to look. This might sound like a weakness, a sign that quantum mechanics is incomplete, but it's actually what gives the theory its power, because the lack of predetermined values means quantum systems can adapt, can explore multiple possibilities, can interfere and recombine in ways that classical systems cannot. Contextuality is what makes quantum computation possible. What allows qubits to hold information in superposition? What lets interference guide probabilities toward correct answers? And contextuality is intimately connected to another principle, one of the oldest and most profound in quantum mechanics: complementarity. Niels Bohr proposed complementarity in the 1920s as a way to reconcile the wave-particle duality of light and matter. He argued that certain properties, though seemingly contradictory, are both necessary to fully describe reality. Light is both a wave and a particle. Position and momentum are both real. Energy and time are both meaningful. But you can never observe both aspects at once. The experiment you perform determines which face of reality you see. This isn't a limitation of technology. It's built into the structure of quantum mechanics. The more precisely you measure position, the less precisely you can know momentum. The more tightly you pin down energy, the less certain you become about time. These pairs of properties are complementary, not contradictory. They don't conflict, they complete each other, but they can never be seen together. Bohr believed complementarity wasn't just a feature of quantum mechanics, it was a lesson about knowledge itself, about the fact that understanding always requires a choice, a perspective, a trade-off. You can ask the universe certain questions, but not all questions at once. And the answers you get depend on which questions you choose to ask. This might feel unsettling. It might feel like the universe is withholding information, playing games, keeping secrets. But it's the opposite. The limits aren't arbitrary. They're protective. They keep the universe consistent. They prevent paradoxes. They ensure that even in a world governed by probability and uncertainty, the rules never contradict themselves. The no-cloning theorem prevents faster-than-light communication. Complementarity preserves the uncertainty principle. Contextuality ensures that quantum mechanics doesn't collapse into hidden variable determinism. Each limit guards against a deeper inconsistency, a crack in the foundation that would make reality impossible. So these aren't weaknesses. They're the architecture of possibility. The universe doesn't forbid cloning, teleportation, or contextuality because it's cruel. It forbids certain things because allowing them would break the elegant symmetry that holds everything together. And here's the beautiful part. Once you accept the limits, once you stop fighting them and start working with them, they become tools. The no-cloning theorem enables unbreakable encryption. Complementarity enables precise sensors. Contextuality enables quantum computing. The boundaries don't cage us. They guide us. They show us what's possible, and just as importantly, what's not. In the end, the limits of the quantum world teach a quiet lesson. That knowledge always comes at a cost. That certainty is a trade-off, not a birthright, and that the universe, in refusing to answer every question, is not being mysterious. It's being honest, because reality at its deepest level is not a fixed script waiting to be read. It's a conversation, and in every conversation, the question you ask shapes the answer you receive. So, the universe has rules, boundaries, limits we cannot cross. But within those limits, we've built something extraordinary. Technologies that harness the quantum world, tools that would have seemed like magic a century ago. And as we stand on the edge of the quantum revolution, one question remains. What comes next? The universe has rules, and we've learned to use them. Every boundary, every limit, every strange quantum principle has become a tool. In fact, you're using them right now. The phone in your hand, the light above your head, the GPS guiding you home, the screen you're reading this on. None of these would exist without quantum mechanics. Not metaphorically, not inspirationally, literally. Every pixel, every circuit, every flash of light is a quiet miracle, a direct application of the strange rules we've been exploring. The quantum world isn't locked away in laboratories or hidden in abstract mathematics. It's here, woven into the fabric of everyday life. And most of the time, you never even notice. Let's start with the transistor, the tiny switch that changed human history. A single computer chip, smaller than your fingernail, can contain tens of billions of transistors. Each one turns currents on and off, faster than any mechanical part could ever move. They're the reason you can carry a supercomputer in your pocket, the reason the internet exists, the reason the modern world functions at all. And transistors work because of quantum mechanics. Inside a semiconductor, electrons don't roam freely like they do in a metal, nor are they locked in place like in an insulator. Instead, they occupy specific energy bands, allowed regions determined by the quantum rules of atoms bonded together in a crystal lattice. Between these bands lies a forbidden region called the band gap, where electrons simply cannot exist. By adding impurities, engineers can tweak how easily electrons jump across that gap, creating materials that behave like one-way streets for current. Apply a small voltage, and you can control whether electrons flow or stop. The result is a device that can switch billions of times per second, amplifying signals, processing information, building the logic gates that power every computer, every smartphone, every satellite. The rules that make quantum mechanics seem weird, discrete energy levels, forbidden zones, quantum tunneling, are the same rules that make digital technology possible. Without them, there would be no laptops, no GPS, no modern civilization. From transistors, it's a short step to light itself. Quantum physics explains how light and matter exchange energy one photon at a time. This is the principle behind LED's light-emitting diodes, which are now so common we rarely pause to consider how extraordinary they are. In an LED, electrons are injected into a semiconductor, where they fall from a higher energy band to a lower one, releasing the difference as a photon. The color of the light depends on the size of the band gap. A small gap gives red, a larger one gives blue. This process is elegantly efficient because every photon is born from a single quantum jump, not from heat or waste. LEDs don't glow by getting hot. They glow by dancing between quantized levels. That's why they last so long, why they consume so little power, and why they've replaced incandescent bulbs almost everywhere. The same idea powers lasers, perhaps the most famous quantum devices of all. The word laser stands for light amplification by stimulated emission of radiation, a process that relies on coaxing electrons into excited states and then encouraging them to fall back in unison, releasing identical photons. Those photons stimulate others to do the same, creating a cascade of perfectly synchronized light waves. The result is coherence light that marches in lockstep each wave, crest aligned with the next. Because of this, precision lasers can cut through steel, carry data through fiber optic cables, scan barcodes, perform delicate eye surgery, and measure distances to the moon with centimeter accuracy. Every smooth red beam you see at a checkout counter or concert is a perfectly tuned quantum chorus singing one note in unison. Solar cells work on the same principle, but in reverse. Instead of turning electrical energy into light, they turn light into electricity. When a photon strikes the surface of a solar panel, its energy can lift an electron across the band gap in a semiconductor, creating a free charge that flows as current. This is the photoelectric effect, the very phenomenon Albert Einstein explained in 1905, earning his Nobel Prize. Each tiny cell on a solar panel is like a miniature photon trap, converting sunlight into electrons that travel down wires to power homes, satellites, and spacecraft. The world's most promising source of renewable energy depends on the quantum dance between light and matter, one photon at a time. If quantum physics governs how we make energy and light, it also governs how we measure time. The ticking of an ordinary clock depends on mechanical motion gears, springs, pendulums. But the ticking of an atomic clock depends on the oscillations of atoms themselves. In the mid-20th century, scientists learned how to use microwave radiation to probe transitions between the energy levels of cesium atoms. These transitions occur with astonishing regularity, 9,192,631,770 cycles per second. Exactly, that number defines the second. Modern atomic clocks are so stable, they lose or gain less than 1 second over the entire age of the universe. GPS systems rely on them to synchronize satellites and calculate precise positions. A timing error of just a few nanoseconds could throw off a location by several meters. So, the global navigation systems guiding planes, ships, and phones all depend on quantum precision. Even the stock market's high-frequency trading algorithms rely on atomic time. Every now in our world, every timestamp, every digital heartbeat is kept in tune by the quiet rhythm of electrons jumping between quantized energy states. Another remarkable application of quantum physics is found inside hospitals. The MRI scanner, short for magnetic resonance imaging, works by probing the quantum property of spin in atomic nuclei, particularly those of hydrogen in the body's water molecules. When placed in a strong magnetic field, these spins align like tiny compass needles. A pulse of radio waves nudges them out of alignment, and as they relax back, they emit faint signals. By detecting those signals and mapping how they vary across tissues, the machine builds detailed images of the body's interior without a single incision. The clarity of those scans, down to millimeters or even less, comes directly from the predictable quantum behavior of nuclear spins in magnetic fields. It's a way of listening to the body's atoms hum their quiet tune. Each of these technologies, transistors, LEDs, lasers, solar cells, atomic clocks, MRI, illustrates the same profound truth. Quantum mechanics isn't confined to laboratories or thought experiments. It's woven into the fabric of everyday life. The lights in your room, the internet, carrying this very sentence, the navigation system guiding you home all depend on electrons leaping between quantized levels and photons following the probabilistic rules, first glimpsed more than a century ago. Even seemingly mundane materials owe their properties to quantum mechanics. The color of metals, the transparency of glass, the hardness of diamonds, all come from the arrangement of electrons in quantized energy bands. The resistance of copper wires, the behavior of magnets, the properties of superconductors, each emerges from the collective behavior of countless particles obeying the same microscopic laws. Every device around you is in its own quiet way a quantum system scaled up and domesticated. And yet, for all its complexity, quantum technology also has a strange elegance. Once you understand how particles share energy and information, the chaos of the world begins to look ordered. A transistor switching in a microchip, a laser emitting coherent light, an atom vibrating in a clock, they all follow the same mathematics. The universe at its smallest scales plays by simple, beautiful rules, and we've learned just enough to borrow them. Looking ahead, the boundary between quantum technology and everyday technology is fading fast. Quantum computers are beginning to perform specialized tasks. Quantum sensors are being developed to detect gravitational waves and underground minerals. Quantum networks may someday enable unhackable communication. But in truth, the quantum revolution has already happened. It began when engineers first learned to shape the energy bands of silicon and capture the light of a single photon. The world around you hums quietly with quantum precision. Every glowing pixel, every electronic pulse, every perfectly timed signal is part of a vast, invisible orchestra. Electrons, photons, and atoms performing their subtle symphony beneath the surface of ordinary life. And that's perhaps the most astonishing part of all. The most exotic physics in the universe isn't hidden in distant galaxies or particle colliders. It's right here humming in your pocket, lighting your room, guiding your way home, reminding you every second that you live in a world built on the smallest possible miracles. Quantum mechanics powers your phone, your lights, your medicine. But that's just the beginning, because we're on the edge of something bigger, a technology so powerful it could reshape everything we know. The quantum world has already changed civilization once. It gave us transistors, lasers, and the digital age. But now we're learning to harness quantum mechanics in a new way, not just to control particles, but to compute with them. In 2019, a quantum processor built by Google performed a specific calculation in about 200 seconds. That same calculation would have taken the world's most powerful supercomputer approximately 10,000 years. This was not a trick. It was not a simulation. It was a real computation solved by a real machine using the actual laws of quantum mechanics. And it marked a turning point, a moment when quantum computing stopped being a distant dream and became something tangible, something that could one day change everything. The power of quantum computers comes from something we've discussed before: superposition. A classical computer bit is either 0 or 1 on or off a simple binary choice. But a qubit, a quantum bit, can be both 0 and 1 at the same time, held in a delicate superposition of possibilities. That alone wouldn't be revolutionary. But here's where it gets extraordinary. 2 qubits can represent 4 states simultaneously. 10 qubits can represent over 1,000. 50 qubits can hold more combinations than there are atoms in the human body. 300 qubits, more than there are atoms in the observable universe. This exponential scaling is what makes quantum computing so tantalizing. It grows in power far faster than classical machines ever could. But superposition alone isn't enough. The real magic happens when qubits become entangled, linked, so that the state of one instantly influences the others, no matter how far apart. When two qubits are entangled, measuring one tells you something about the other, even before you check. In a quantum computer, this allows information to spread across the entire system in ways that classical bits can't replicate. Entangling operations, known as quantum gates, create intricate webs of correlation, letting the computer process multiple layers of information at once. Entanglement isn't just a neat trick, it's the glue that makes quantum algorithms work. When qubits are entangled, the system as a whole becomes more than the sum of its parts. This interconnectedness allows quantum computers to manipulate probability itself, sculpting the outcomes through interference. In essence, the computer sets up a series of quantum waves representing all possible answers to a problem, then cleverly arranges the computation so that the wrong answers interfere destructively while the right ones reinforce each other. When the system is finally measured, the quantum haze collapses not into chaos, but into the most likely correct solution. This is how quantum algorithms differ from classical ones. A classical algorithm walks step by step like a detective following a trail. A quantum algorithm lets all possible paths be explored at once, then uses interference to highlight the path that leads to the right conclusion. It's a kind of computational parallelism that doesn't just make things faster, it changes the rules of what's possible to compute. For example, Shor's algorithm can factor large numbers exponentially faster than any known classical method, threatening to upend modern encryption. Grover's algorithm can search through unstructured data far more efficiently, and newer quantum algorithms promise breakthroughs in chemistry optimization and even the simulation of quantum systems themselves, tasks where classical computers simply run out of time. But the quantum world is fragile. Superposition and entanglement don't last long before decoherence. The loss of quantum order sets in. The smallest disturbance from the environment, a stray vibration, a flicker of heat can collapse the delicate quantum state and destroy the information. That's where quantum error correction comes, in one of the most ingenious ideas in modern science. In classical computing, error correction is straightforward. Copy the data, compare the copies, fix discrepancies. But in quantum computing, the no-cloning theorem forbids making exact duplicates of unknown quantum states. Instead, physicists found a way to encode one logical qubit into many physical qubits, distributing the information in such a way that small errors can be detected and corrected without disturbing the computation. It's like hiding a secret inside an orchestra. Even if one musician plays the wrong note, the melody can still be reconstructed from the others. Quantum error correction is what makes large-scale quantum computing possible in theory. Without it, qubits would lose coherence too quickly to perform meaningful work. With it, quantum computers could one day run for hours or even days, solving problems that are utterly intractable for classical machines. The current frontier of research isn't just about making more qubits. It's about making better qubits with longer coherence times, higher fidelity, and better protection from noise. Different technologies have emerged in this race. Superconducting qubits made from Josephson junctions are among the leading contenders used by companies like IBM and Google. They operate at temperatures just a few thousandths of a degree above absolute zero, where electrons flow without resistance. Trapped ion qubits, on the other hand, use individual atoms suspended in electromagnetic fields manipulated by laser pulses. They're incredibly stable and precise, though slower to operate. Other approaches like photonic qubits, made of light, or topological qubits, designed to be inherently fault-tolerant, represent the cutting edge of quantum engineering. Each has strengths and weaknesses, and no one knows yet which will dominate the future. What's striking is how closely quantum computing mirrors the principles of nature itself. The universe doesn't compute outcomes by testing them one at a time. It allows all possibilities to coexist, then interferes them through the laws of physics to produce reality as we experience it. Quantum computers, in their own way, are designed to harness that same natural efficiency. They don't replace classical computers. They complement them, opening doors to problems where the classical approach simply runs out of time. Even in its infancy, quantum computing has already proven its potential. That 2019 Google experiment, though designed for demonstration rather than utility, proved the principle. Quantum devices can reach realms of computation that classical ones cannot touch. Since then, the field has only accelerated, with researchers increasing qubit counts, reducing errors, and exploring new architectures that inch closer to practical quantum advantage. But beyond the technology, there's something deeply poetic about the idea. A qubit suspended between 0 and 1 embodies uncertainty, not as a flaw, but as power. Where classical computing relies on certainty, quantum computing thrives on possibility. It uses the fuzziness of the quantum world, not as a limitation, but as a tool. Every calculation is a negotiation between what could happen and what must, a symphony of probabilities orchestrated into precision. Beyond computation, the quantum future holds other promises. Quantum communication networks built on entanglement could link cities and continents in unhackable channels. Quantum sensors exploiting superposition and interference could detect gravitational waves from the Big Bang map, underground water reserves, or diagnose diseases by sensing the faintest molecular changes in the body. The applications stretch into medicine materials, science, artificial intelligence, climate modeling fields, where complexity overwhelms classical methods, but where quantum systems could thrive. We're not just building faster computers, we're learning to think the way the universe thinks, parallel, probabilistic, and profoundly interconnected. If the 20th century was defined by mastering the electron, the 21st may be defined by mastering its uncertainty. Quantum computers are still fragile, expensive, and experimental, but their promise is immense. The ability to simulate chemistry at the molecular level, optimize complex networks, crack problems that have stood unsolved for decades, and perhaps even uncover new laws of nature. In every sense, they are humanity's attempt to partner with the quantum world, to stop fighting its strangeness and start dancing with it. One day, when quantum computers become as commonplace as laptops, we may look back on the qubit the way we now look at the transistor, the simplest possible object that changed everything. But for now, it remains something extraordinary, a single, silent unit of possibility, holding 0 and one together in the same breath, waiting to decide what reality will be. So the future is quantum. But after all we've learned, after all the strangeness and beauty, what does it all mean? What have we really discovered about the universe and about ourselves? We've traveled through a world of superposition, entanglement, and invisible fields. We've seen particles that are waves empty space, that hums with energy, and a universe woven from probability. But now it's time to step back, to ask the final question. What have we learned? After 100 years of research, after millions of experiments, after thousands of pages of mathematics, after building technologies that power the modern world, after staring into the quantum abyss and watching it stare back, what have we learned? The answer is both simple and profound. Reality is not what you think it is, not solid, not separate, not certain. The world you touch the light, you see the ground beneath your feet. None of it exists the way your senses suggest. Matter is mostly empty space, held together by forces you can't see. The objects around you aren't really touching. They're hovering suspended on invisible cushions of quantum repulsion. Every surface is a lie. Every sensation is an illusion carefully constructed by your brain from signals that never directly contact the thing they describe. And yet, the illusion is consistent, reliable, predictable. The quantum rules, strange as they are, never break. They've been tested to 1 part in a trillion and never once failed. The universe may be weird, but it's not chaotic. Beneath the uncertainty lies a deeper order, a mathematical harmony so precise that we can build entire civilizations on it. Observation matters, not because consciousness is magical, but because interaction defines reality. Before measurement, a quantum system exists. In superposition, a cloud of possibilities. After measurement, one outcome emerges, not because it was always there, but because the interaction forced a choice. You are not a passive observer watching the universe unfold. You are a participant entangled with everything you touch, shaping reality simply by being part of it. The boundary between observer and observed dissolves. There is no outside. You can't step back and see the universe objectively because you're always already inside it, influencing it, becoming part of its wave function. Quantum mechanics teaches humility. It reminds us that we are not separate from the world. We are notes in the same song. Limits create possibility. The no cloning theorem makes quantum cryptography secure. The uncertainty principle keeps atoms stable. Complementarity balances knowledge, ensuring that you can know position or momentum, energy or time, but never both with perfect precision. These aren't flaws, they're features. The universe doesn't withhold information out of spite. It enforces boundaries to prevent paradoxes, to keep reality consistent, to ensure that the game remains playable. Every rule is a gift. Every restriction opens a door. The quantum world teaches us that constraints don't cage us. They guide us. They show us not just what's possible, but what's beautiful. The universe is one thing, not a collection of separate objects, but a single unified web of relationships. Entanglement stretches across galaxies, linking particles that have never met. Fields extend everywhere, vibrating in harmony, creating the illusion of separateness when really everything is connected. You and the stars, you and the ground, you and the photons that left the sun 8 minutes ago and are only now touching your skin. distance is real in one sense, but in another deeper sense, it's an illusion. The universe doesn't have parts, it has patterns, and you're one of those patterns. Not a solid object, but a wave, a temporary ripple in the electron field, the quark field, the Higgs field. You're not made of atoms. You're made of information, of relationships, of probabilities that briefly coalesce into something that feels like you. And when you die, the pattern dissolves, but the fields remain waiting to vibrate again, to form new patterns, new songs, new stories. But even after all this mystery remains, we've learned to calculate, we've learned to predict, we've learned to build, but we still don't fully understand why. Why does measurement collapse the wave function? What is the wave function really? Is it physical or just a tool? Do parallel universes exist? Or is reality singular? Does the universe need observers? Or does it unfold? Whether anyone watches or not, no one knows. And perhaps in a strange way, that's perfect, because it means the deepest question of all, what is real, is still being asked, still being explored, still inviting us to look closer, think harder, and wonder. The quantum world doesn't hand us certainty. It offers a framework, a language, a way to navigate the mystery. And that's enough. That's everything. So what have we learned? We've learned that the universe is stranger than fiction, but more beautiful than poetry. That reality is woven from waves, and probabilities that matter is mostly emptiness, held together by refusal, that light is both particle and wave, that observation shapes outcome, that entanglement defies distance, and that the smallest things, the things we can't see or touch, govern everything. We've learned that you don't touch anything, you never have. But the forces that keep you from falling through the floor, the quantum pressures that hold your atoms together, are just as real as any touch could ever be. We've learned that you are not separate from the world. You are the world briefly aware of itself. And we've learned that the universe, for all its mystery, is not silent. It hums, it vibrates, it sings. And if you listen closely enough, if you learn its language, you can hear the song. You can join it. You can become part of the harmony. That's the final lesson. Quantum mechanics isn't just a theory. It's an invitation to see the world not as it appears, but as it is. To embrace uncertainty, not as ignorance, but as openness. To recognize that the boundaries we see between self and other, between wave and particle, between known and unknown, are softer than we think. The universe is not a machine grinding forward in perfect order. It's a conversation, a dance, a symphony still being composed. And you, reading this, breathing, thinking, wondering you are one of its instruments. So when you leave this video and return to the normal world, remember everything you touch isn't real. The light you see lies. The particles in your body are connected to the stars. And the phone in your hand is a quantum miracle, humming with the same laws that govern galaxies. You're not a pile of atoms standing still. You're a wave dancing through the quantum symphony of existence. And that perhaps is the most beautiful truth of all. Thank you for drifting through the quantum world with me tonight. If this journey bent your mind just a little, if it left you with new questions or quiet wonder, please give the video a like. It helps more curious minds find their way here. Subscribe to my channel for for more calm explorations of the universe, and hit the bell so you won't miss the next journey. Until then, sleep well, and remember, you're not just in the universe, you are the universe, dreaming